Hello, Year 12. Today's lesson in the unit of quantum physics is basically going through some past exam questions, okay, talking you through the workings out, how I work them out, and hopefully you will have had a chance to have had a go at these first, and then we'll come to look at these afterwards. Today's questions are on the photoelectric effect, and this is a very important topic, as I mentioned, within the unit. It's a favourite of the examiners, I think, because it seems to come up very often. Okay, so do prepare for this. I think one of the best ways to prepare is to practice the questions as much as you can, and the more questions you do and do them a few times over and over again, the more you will get used to it and familiar with it, and I'm sure that it will become much easier, okay, because you'll find a lot of the things are very similar to what you've already done before once you've done them a few times. So question number one, electromagnetic radiation is incident on a metal. The radiation has constant wavelength, with each photon having an energy of 5 electron volts. The work function of the metal is 3 electron volts. Which of the following cannot be the kinetic energy of an emitted photoelectron? So one of the other pieces of advice I'd give you is if you want to do this, you can underline key words as well, and you can underline key quantities. So here we have some key quantities of the energy of the photon and the work function of the metal. Both are in electron volts, so that's key. We don't need to change any of them into joules because they're both in the same energy unit. Which of the following cannot be the kinetic energy of an emitted photoelectron? Okay, so we can picture our photoelectrons trapped in an energy well. A single electron requires a minimum energy given by the work function shown as phi to escape the surface of the metal. By the conservation of energy, there will be a range of kinetic energies up to a maximum value, which is given here as Ke electron max. Okay, there we can see the incoming photon, and the energy of the photon must be equal to the work function, okay, and added to the maximum kinetic energy of the photoelectron. So that is the photoelectric equation, Einstein's photoelectric equation. So we can substitute in our values. We get 5 is equal to 3 plus the kinetic energy of the electron max. Substitute the 3 from 5, so we get 5 take away 3 is equal to the kinetic energy of the electron max, which is equal to 2 electron volts. So that is the maximum kinetic energy of the electron. So that means that anything over 2 electron volts is not possible. Anything equal to or under 2 electron volts is possible. So because there will be a range of kinetic energies up to that maximum value. So that straight away rules out D, which is given as 3 electron volts. It's just not possible. The maximum that's possible is 2 electron volts. So the kinetic energy can be anywhere between 0 electron volts and 2 electron volts, but no more. So the answer is D. Question number 2, another multiple choice question. Photons of energy 4.8 times 10 to the power minus 19 joules are incident on the surface of a clean metal plate of work function 3.2 times 10 to the power minus 19 joules. What is the maximum speed of emitted electron? So this one is one of those questions where you've got to be really fast, because if you're out of practice or you haven't practiced this question, then it can take a little bit of time. So make sure that you practice these types of questions, because you only have a very short time to do them in. Okay, so the values that we're given are 4.8 times 10 to the power minus 19, which is equal to the energy of the photon, which is also equal to Hf. The work function is 3.2 times 10 to the power minus 19 joules. And again, the good thing is that both of these quantities are given in joules, so there's no conversions that need to be done. Okay, so we use Einstein's photoelectric equation. The energy of a photon is equal to the work function plus the maximum kinetic energy. So if we rearrange that, so we do the energy of a photon minus the work function is equal to the kinetic energy max. And then if we do substitute in our numbers, 4.8 times 10 to the power minus 19, take away 3.2 times 10 to the power minus 19. That's quite straightforward because the powers are both to the minus 19. So we just do 4.8 take away 3.2, which gives us 1.6 times 10 to the power minus 19 joules. And then we are going to equate that to half mv squared max. Okay. So in order to get V max, we just need to take the square root of everything on the left-hand side of the equation. We multiplied both sides of the equation by 2 to get rid of the half next to the half mv squared. And we also divided both sides of the equation by m. Now, m is the mass of the electron, and this is given in your equation sheet in the exam. Okay, so the value of the mass of an electron is 9.1 times 10 to the power minus 31. Okay, so that's in kilograms. Right, so we do 2 times 1.6 times 10 to the power minus 19 divided by 9.1 times 10 to the power minus 31. All of that under the square root, and that gives us V max, and V max is 5.92 times 10 to the power 5 meters per second, which is approximately 5.9 times 10 to the power 5 meters per second. So that tells us that our answer is most certainly A. Question number 3, another multiple choice question. Violet light is incident on the surface of a metal. Photoelectrons are emitted from the surface of the metal. The frequency of the radiation incident on this metal is increased, but the intensity of the radiation is kept constant. Which statement is correct? So we have violet light photons incident on a metal surface, causing photoelectrons to be emitted from the metal surface. The important thing to note is that the frequency is increasing. So the value of the Planck constant increases. Well, Planck's constant is a fundamental physical constant, so that's certainly not true. The work function of the metal increases. Well, the work function is constant for a particular metal. We're not changing the type of metal, so that statement is false. C, the number of photoelectrons emitted per second increases. Now, the number of photoelectrons emitted per second is the intensity, but this does not change according to the question. So that leaves us with D, the only possibility to be correct. The higher frequency means higher energy of the photons. Okay, that's the key thing, because the energy is directly proportional to the frequency. So the answer is D. Question number 4. In a demonstration experiment of the photoelectric effect, light of wavelength 440 nanometers incident on a clean metal surface causes electrons to be emitted. No electrons are emitted from the surface when the wavelength of the incident light is greater than 550 nanometers. The first question, define the term work function, comes up quite a lot. You must know it. It's not always worth 2 marks. I've seen it worth 1 mark as well. But if they ask you to define it, you must cover these points regardless. Okay, so the work function is the minimum energy needed to liberate a photoelectron from the metal surface. Now you must make sure that you mention that it's the minimum energy needed. Okay, it's also very important to say that it's from the surface of the metal, as opposed to saying that it's from inside the atom. Okay, it's not, it's the metal surface, so we should mention that as well. Okay, part 2 says explain how the work function is related to the threshold frequency. So if a photon strikes a metal surface at a threshold frequency f0 for that particular metal, it will only have enough energy to free a surface electron with none left over to be transferred into the kinetic energy of the photoelectron. So there'll be no kinetic energy of the photoelectron. In other words, if the photon has less frequency than the threshold frequency F0, then it cannot cause electron emission. Okay, so we can simplify the photoelectric equation, and we can say that the work function phi is simply equal to Hf0. Okay. And part 3, calculate the value of the work function for this metal. Now there's two numbers given. There's light of wavelength 440 nanometers, and there's incident light of wavelength 550 nanometers. Now this will sometimes throw people, and we've got to make sure that we get the right one. So 550 nanometers causes emission of light. After 550 nanometers, no photoelectrons can be emitted. So it is the 550 nanometers that we need to use, okay, because it's asking us for the work function of the metal. Any wavelength greater than 550 nanometers won't work, okay, so we have to choose 550. Okay, so that will give us the value of the work function. So the work function is equal to Hf0, which is also equal to Hc over lambda naught, because we don't have the frequency, but we're given the wavelength. So the work function is equal to 6.63 times 10 to the power minus 34 multiplied by 3 times 10 to the power 8, the speed of light, divided by 550 times 10 to the power minus 9 meters, which is the wavelength of the incident light, and that is equal to 3.6 times 10 to the power minus 19 joules. Okay, now it's just very important that we remember that when we're talking about the work function, we're talking about the electron energy. When we're talking about the threshold frequency, we're referring to the photon energy. Okay. Question number 5a, which is worth 4 marks. Einstein derived the following equation to explain the photoelectric effect. Hf is equal to phi plus Ke max, electromagnetic radiation of frequency 1.2 times 10 to the power 15 Hertz is incident on the surface of a negatively charged aluminium plate. The work function of aluminium is 4.1 electron volts. Part 1. Show that the maximum speed of the electrons emitted from the surface of the aluminium is 5.5 times 10 to the power 5 meters per second. It's quite a nice question when they actually give you the answer, and you have to make sure that you're working out tallies with this particular answer. So you can either underline the key terms or you can write them out. I recommend that you underline them to save time. F, the frequency, is equal to 1.2 times 10 to the power 15 Hertz. The work function is equal to 4.1 electron volts. Planck's constant is equal to 6.63 times 10 to the power minus 34 joules second. So we have the photoelectric equation. I'm just replacing kinetic energy max with half mv squared, okay, in that equation. Now I need to convert the work function, which is given in electron volts, into joules because I have Planck's constant in joules second. So in order to convert from electron volts to joules, I need to multiply by 1.6 times 10 to the power minus 19 joules. So the work function is equal to 4.1 times 1.6 times 10 to the power minus 19 joules, which gives me the work function to be 6.56 times 10 to the power minus 19 joules. Then I substitute those numbers into Einstein's photoelectric equation. So 6.63 times 10 to the power minus 34, which is Planck's constant, multiplied by the frequency, 1.2 times 10 to the power 15, is equal to the work function, 6.56 times 10 to the power minus 19, plus a half mv squared max. Now, bringing the work function value onto the left-hand side of the equation and subtracting it from the product of Hf, we are left with 7.956 times 10 to the power minus 19, take away 6.56 times 10 to the power minus 19, which is equal to half mv squared max. Because the powers are the same, we can just do 7.956, take away 6.56, and we are left with 1.396 times 10 to the power minus 19, which is equal to half mv squared max. Then if we multiply both sides of the equation by 2 and divide both sides of the equation by m, and that little postscript there is electrons, so it's the mass of an electron, and that is also given in the equation sheet. Okay, so we have 2 times 1.396 times 10 to the power minus 19 divided by the mass of an electron, which is equal to v squared max. Taking the square root, we will get v max, so v max is equal to 2 times 1.396 times 10 to the power minus 19 divided by the mass of the electron, which is 9.11 times 10 to the power minus 31, all square rooted, and that gives us 5.54 times 10 to the power 5 meters per second, which is indeed 5.5 times 10 to the power 5 meters per second. Part 2, which is worth 2 marks. State and explain what change, if any, occurs to the maximum speed of the emitted electrons when the intensity of the electromagnetic radiation is increased. That little bit there that says if any is a bit of a hint actually to the sort of answer that we expect as well. So increasing the light intensity of the electromagnetic radiation would have no effect on the kinetic energy of the emitted electrons, and therefore no effect on the speed of the emitted electrons, because we know that the kinetic energy is directly proportional to the square of the velocity. So what can we write? We could say that the maximum energy of the photoelectrons is independent of the intensity of the electromagnetic radiation, the incident radiation. Okay, the number of photons has increased, but the energy of each photon is the same because intensity is the number of photons per second. The energy of a photon is only dependent on the frequency. So the energy of a photon is directly proportional to the frequency, and that comes from the equation as well, which is E is equal to Hf. The intensity affects the number of photons and therefore the number of emitted electrons only. Okay. The frequency of a photon has not changed. B is a nice, easy question, just as long as you can make sure that you remember the definitions. Define the following terms from the equation. So the equation Hf, well, that is simply the energy of a photon. The work function, we've done that before, haven't we? So there's no harm in having another go, just to make sure that you have remembered it. So work function phi is the minimum energy required to remove a single photoelectron from the metal surface. Okay, and it's as simple as that. Question number 6, this is the 6-mark question, and it's about the photoelectric effect experiment. There are a lot of questions on the actual experiment, and sometimes you have to draw a diagram, sometimes you have to describe the experiment. In this case, the experimental observations provided, you have to just interpret these observations, and you have to look at the development of the particulate nature of electromagnetic radiation, as the wave theory couldn't explain what was happening from these observations. So the question is, a gold leaf electroscope is used to demonstrate the photoelectric effect. A zinc plate is placed on top of the electroscope. The zinc plate is negatively charged, as shown in figure 7. This question is interesting in the sense that they haven't mentioned that the zinc plate is cleaned, but it's probably been cleaned prior to being charged. So white light from a table lamp is allowed to fall onto the electroscope from a distance of 10 centimeters. The experiment is then repeated with light from a distance of 4 centimeters. Both experiments are then repeated with ultraviolet radiation. The electroscope is fully charged before each experiment. Okay, The other important thing also to note here is that you may recall when we looked at the experiment when it was done, it only worked for when the zinc plate was negatively charged. When it was positively charged, it didn't work. Okay, and we already recall that it didn't work for visible light. Didn't matter what intensity we or how bright it was. Okay, so here's the results. The observations are recorded in table 7. So we have incident radiation, light at a distance of 10 centimeters. The observations were that the gold leaf takes a very long time to fall. Essentially, it won't fall for quite a while, so there'll be no effect, essentially. Okay, the second one, light at a distance of 4 centimeters, so we're increasing the intensity. Gold leaf takes a very long time to fall, so no difference there. Suddenly we bring in ultraviolet radiation at a distance of 10 centimeters, so pretty far, and the gold leaf falls quickly. Then we bring the ultraviolet radiation at a distance of just 4 centimeters, so increasing the intensity, and the gold leaf falls very quickly. Okay, so explain how these observations demonstrate the photoelectric effect and provide evidence for the particulate nature of electromagnetic radiation. Now, if you want to look at the observations and the photon model in explaining those observations in more detail, as well as what the wave theory was telling us as well. If you go to slide 7 of the second PowerPoint lesson on the photoelectric effect, and the title of that slide is The Success of the Photon Model in Explaining the Photoelectric Effect, then you can certainly get more information there. I'm going to try to answer this question in 2 segments. I'm going to look at or talk about the observations first, or what we can interpret from the observations, and then look at the particulate nature of EM radiation. Okay, so the first observation is that the discharge of the gold leaf occurs due to the emission of photoelectrons. Okay, so the overall negative charge is being lost, and so the gold leaf starts to drop or hang. Okay. The second point is that the intensity of the incident photons depends on the distance. Okay, the closer it is, the more intense radiation we have. Okay, the smaller the distance, the greater intensity or rate of incident UV photons that fall on the surface of the metal. Yes, because we saw that the smaller the distance, the quicker, in the case of the UV light, the quicker the gold leaf fell, so it discharged quicker, so the rate of photoelectrons emitted was also higher as well. The UV photons cause instantaneous discharge. There is no effect with white light, regardless of whether the light intensity is increased, as we saw in the observations there. Okay. Now we can look at the particulate nature of electromagnetic radiation. We can just begin by talking about the wave theory, which suggests that low frequency light should cause the emission of electrons, photoelectrons, so the leaf would fall with light shone upon it. Yes. Photon is a packet of energy, and low frequency light has energy too small to release a photoelectron. Okay. There is a one-to-one interaction between a photon and an electron. So a single photon is enough to release a single electron. A few more points that we can make about the particulate nature of electromagnetic radiation, namely that the UV photons have greater energy than the work function or greater frequency than the threshold frequency. Light photons have less energy than the work function. E is equal to Hf, so photon energy depends on the frequency. The higher frequency means more energetic photons, so the electrons can move faster and gain more energy. The energy of a photon is independent of intensity, so greater intensity doesn't mean more energetic photons, just more photons arriving at the surface per second, so electrons cannot have more energy. Low intensity light means fewer photons, not low energy photons. Energy is conserved in this interaction, and we can write Einstein's photoelectric equation as well. Hf is equal to phi plus Ke max. The energy of a photon is the minimum energy required to free a single photoelectron from the surface of the metal, plus the maximum kinetic energy of the emitted electron. So the effect of increasing intensity is related to the rate at which photons are absorbed by the plate. Okay. Question number 7 is also a 6-mark question. Two groups of researchers, A and B, conduct photoelectric effect experiments on a new material. The maximum kinetic energy, Ke max, of the photoelectrons emitted from the material is determined for different frequencies f of the electromagnetic radiation incident on the material. Figure 19 shows incomplete graphs of Ke max against f from the groups A and B. So this is something that we have looked at in our earlier lessons on the photoelectric effect. We've looked at graphs of Ke max against frequency. So the question goes on to say the value of the Planck constant h is determined from the completed Ke max against f graphs. The result from each group is shown below. So group A found Planck's constant to be 6.3 plus or minus 0.3 times 10 to the power minus 34 joules second. Group B found Planck's constant to be 6.6 plus or minus 0.6 times 10 to the power minus 34 joules second. So some very important information there. Explain how a graph of Ke max against f can be used to determine h. That's the first thing we need to do. Then we've got to discuss the accuracy and precision of the results from each group. So we can look at the values for h, and we can also look at the data plotted on the two graphs as well for that discussion. The first thing that we need to do is write down Einstein's photoelectric equation, which is Hf is equal to phi plus Ke max, and we need to write that a graph of Ke max against f, the frequency, is a straight line graph. Okay, we know the equation of a straight line is y is equal to mx plus c. If we rearrange the photoelectric equation to make Ke max the subject of it, then we are having Ke max is equal to Hf minus phi. So the range of y values are the kinetic energy max, and the gradient gives the Planck's constant, and the range of frequency values are plotted on the x-axis, and the y-intercept is minus phi. So the important thing to note there is that the gradient is equal to Planck's constant, and the y-intercept is equal to minus the work function. And then we need to say that we would draw a straight line of best fit through the points and determine the gradient using a large triangle to cover our range of data. Okay, so I am just drawing in the lines. You wouldn't have to do that in the exam. You would have by now 3 marks, okay? But I've just drawn the lines in because it will help to focus your minds on those graphs, which we will need when we're analysing this data, okay, to talk about the accuracy of these results. So what we need to do is we need to work out the percentage uncertainty for A, which is equal to the absolute uncertainty divided by the reading or the value, multiply that by 100, and we get 0.3 times 10 to the power minus 34 divided by the value, 6.3 times 10 to the power minus 34, which gives us a percentage uncertainty of 4.8%. We do the same for group B. they have a percentage uncertainty given by 0.6 times 10 to the power minus 34 divided by, and that should be 6.6 times 10 to the power minus 34, not 6.3, and that gives us a percentage uncertainty of 9.5%. Okay, now we can analyze the accuracy and precision of these sets of data. So the data points for group B are widely spread out, and we can see that by looking at the graph, and that's why I drew the line, because we can see that the points are quite far away from our line of best fit. For B, group B, the value of H is accurate. Why is it accurate? Because it's closer to the real or actual value of Planck's constant, which is 6.63 times 10 to the power minus 34. But the results are not precise. And if they're not precise, it means that they are spread out. Okay. As for group B, the value of H is inaccurate because it's further from the real value. Okay. They got 6.3 times 10 to the power minus 34, and that's further from the real value. But the results are precise because we have a smaller uncertainty value, a percentage uncertainty, and also because the data is less spread out, okay, compared to group B. All right, and that would give us our 6 marks. Okay, so I think we can do this. We can get all the marks. Okay. Question number 8. I think this is a straightforward question. I hope you agree. In an experiment to demonstrate the photoelectric effect, electromagnetic waves are incident on a silver surface. Figure 6 shows the variation with frequency f of the maximum kinetic energy Ke max of the photoelectrons. So not such a dissimilar question to the previous one. We have to define the term threshold frequency, another very important definition that we've looked at. How do we write this out in the easiest possible way? The threshold frequency F0 is the lowest or minimum frequency of the incident photons that release a photoelectron from the surface of silver. Okay, so make sure that you say that it's the minimum, okay, or lowest frequency. All right, it's worth 1 mark. Sometimes I've seen them worth 2 marks. Okay, you could also underline and make sure you say that it's from the surface of silver. Okay. Part 2, use figure 6 to state the threshold frequency F0 for silver. So we need to look at the graph very carefully, and F0 is where the Ke max is 0. Okay, so it's where the line crosses the x-axis. Okay, so I've highlighted that there, and that should tell us that our F0 threshold frequency is 1.1 times 10 to the power 15 hertz. Now, just make sure that you read what's written on the frequency axis in terms of the units and the power as well, the power in particular, because it's 10 to the power 15, so we don't just want to write 1.1. We must make sure that we write 1.1 times 10 to the power 15 hertz. Okay. Remember, at the threshold frequency, F0 Ke max is equal to 0. Part 3, use your answer in part 2 to calculate the work function phi of silver. Give your answer in electron volts. So we need to write our important photoelectric equation. Phi is equal to Hf0 plus Ke max. Now Ke max is 0 at the threshold frequency, so we just have phi is equal to Hf0, which is equal to 6.63 times 10 to the power minus 34 times 1.1 times 10 to the power 15, which is equal to 7.293 times 10 to the power minus 19 joules. But it was worth underlining the fact that we had to give our answer in electron volts. Okay, so to go from joules to electron volts, we must divide by 1.6 times 10 to the power minus 19. So we have 7.293 times 10 to the power minus 19 divided by 1.6 times 10 to the power minus 19. The 10 to the power minus 19 cancel out, and we are left with 4.6 electron volts. Question 8, part A, and just this part is worth 5 marks. In 1905, Einstein presented a theory to explain the photoelectric effect using the concept of quantization of radiation proposed by Planck in 1900. Part A. Show, with the aid of suitably labeled diagram, the arrangement of apparatus that could be used to demonstrate the photoelectric effect. Describe how you would use the apparatus and what would be observed. In your answer, you should make clear how your observations provide evidence for the photoelectric effect. So quite a lot of clues are given as to what we need to do. So we need to have a labeled diagram. So here is our diagram. You have a gold leaf electroscope. You shine some ultraviolet light onto it. Everything is all charged up. Let's say it's negatively charged, because we know that when it's negatively charged, then photoelectrons will be emitted. The whole thing is negatively charged, so the gold leaf will be repelled from the conducting stem. Some of the negative charges have left the gold leaf. Okay, so what can we say? In our diagram, we must make sure that we labeled the key things. I've indicated that it's negatively charged with these minus signs. Okay, I've shown the UV light photons coming in, and I've also put a little arrow on the gold leaf to show that it will hang down. So the first thing to say is, if you have UV light shone on a negatively charged zinc plate, the gold leaf that is initially repelled hangs down. Okay. Third thing is the electrons are emitted from the zinc surface. When you shine certain frequencies of light at a metal surface, photoelectrons are emitted as the gold leaf falls down. For photoelectrons have left the electroscope. Okay, they've been emitted, and so this gold leaf electroscope has become discharged. And that's probably at about 2 marks for the diagram and maybe 3 marks for the observations. Okay. Part B is also worth 5 marks. Describe how the photoelectric effect can be explained in terms of the physics of quantum behavior. Okay, so it's sort of the particulate nature of electromagnetic radiation revisited. So, individual photons absorbed by the electrons on the metal surface. Okay, that's the first key thing, and remember it's the metal surface. One particle of light is absorbed by one electron. Remember, we're talking about electrons on that metal surface, okay, on the surface of the metal. The energy of an incident photon must be greater than the work function of the metal. Now, zinc has quite a low value for the work function, which is why zinc is often used in our electroscopes. Okay. The next thing to note is that a photoelectron is released. Now, the number of electrons emitted is directly proportional to the light intensity, or the number of photons per second. If you were to double the amount of photons landing on the surface above the threshold frequency f0, then you would also double the amount of photoelectrons being emitted from the surface of the metal. So a higher rate of photons landing means a higher rate of electrons escaping, and that can be shown by this diagram here. Okay, there we see that we doubled the number of photons, we simply double the number of electrons. Okay, remember it's one-to-one interaction, so one photon causes the emission of one electron. Okay, as long as we are above the threshold frequency. Okay, and then the other all-important thing to mention always is Einstein's photoelectric equation. Hf is equal to phi plus Ke max, sometimes written as Ek. And Hf is the energy of the photon, which is equal to the work function, plus the maximum kinetic energy of a photoelectron. This is Einstein's photoelectric equation. And there we have our 5 marks. Question number 10. This is quite a nice and interesting question, actually. The kinetic energy possessed by an individual photoelectron never exceeds Ek max. Figure 1 shows how Ek max varies as the frequency of the light F is increased. So here we have our old familiar graph again of Ek max against the frequency. So part A is asking us, explain why no photoelectrons are emitted unless F is greater than the threshold value. Okay, so we could say below the threshold frequency F0, the photon energy Hf is less than the metal's work function, and that would be enough for 1 mark. But if they asked us just to explain this in a little bit more detail or describe it, we could say that below this frequency, the photon's energy is less than that required to break the electron's bond to the positive metal ions due to the electrostatic forces of attraction and release it from the surface of the metal. Okay, that's a little bit more of an explanation. Part B is quite a challenging question, and so I'm surprised that it's worth only 1 mark, especially as they're also saying that they want us to explain this. Explain why the kinetic energy of most photoelectrons is less than Ek max. A very important question as well. I think it helps in the understanding of what is actually happening. So what we could say is photoelectrons are likely to lose energy in collisions as they leave the metal if they are deeper in the metal, because as we know, all the photoelectrons are not necessarily on the surface of the metal. Okay, so actually it's a lot rarer to get electrons with the Ek max. So let's go into a little bit more detail with this. You don't have to draw such a diagram, especially when it's only worth 1 mark, but just to explain it to you, maybe to make it a bit clearer, what we have here is the metal, and we have the large circles representing the ions inside the metal, and we have these photons, incoming photons coming in. Let's say that the UV photons, and maybe that's zinc, and we have lots of electrons inside, free electrons in many cases. And then we have these 4 very important photoelectrons that I've labeled 1, 2, 3, and 4. And those are the ones that we want to follow. They're all going to give different scenarios or different outcomes. And most of them are not going to be able to get near the kinetic energy max, and we're going to look at why. So let's take a look at electron number 1. Electron 1 is, as we can see, at the surface and requires the least possible energy to liberate it. So it escapes with the maximum kinetic energy. That's all nice and straightforward, but that doesn't happen very often. Electron 2, on the other hand, as we can see, is deep within the metal, and it has lost so much kinetic energy by the time it reaches the surface that it is attracted back. Okay, so it doesn't actually escape, unfortunately. On the other hand, electron 3 is slightly deeper than electron 1, and so it escapes, but it escapes with slightly less energy than electron 1, as you can see. Now, if you look at electron 4, it's a completely different, it's on a different story. It gains enough energy to escape, but is moving in the wrong direction and is therefore absorbed by the metal. Okay, so that's why you can see there that out of the 4 electrons I've shown, only 1 emerges with the Ek max. All right, so that's just a bit more of an understanding and background behind why the kinetic energy of most photoelectrons is less than Ek max. Okay, now using figure 1, determine the work function of the metal. Okay, so for this one, what we need to do is that we need to take the work function. How do we find the work function? It can be found by extending the line of best fit and seeing where it crosses the y-axis. So let's do that. So we'll do that on our graph. And what we find is that the y-axis point where the line crosses is 3.6 electron volts. Part D. Calculate the maximum speed of a photoelectron emitted when 9.3 times 10 to the power 14 hertz of light is incident on the metal. Now, the first thing we're going to have to do is convert our work function into joules, because we're going to have Planck's constant, which is given in joules second. So the work function, from electron volts to joules, we need to multiply by 1.6 times 10 to the power minus 19. So we get 3.6 times 1.6 times 10 to the power minus 19 joules is equal to 5.76 times 10 to the power minus 19 joules. Then we need to calculate EK max, and we need to remember that Einstein's photoelectric equation Hf is equal to EK max plus the work function. Now we want to make EK max the subject of the equation, okay, because within EK max is a half mv squared. So EK max is equal to Hf minus 5. So EK max, plugging in the numbers, is equal to 6.63 times 10 to the power minus 34 times 9.3 times 10 to the power 14. Multiply those out together and then take away 5.76 times 10 to the power minus 19, which is the work function in joules. And that gives us EK max of 4.059 times 10 to the power minus 20 joules. So we then remember that EK max is equal to a half mv squared max. If we take the square root of 2 EK max and divide that by me, which is the mass of an electron, that is equal to V max. And then plugging in our numbers, the square root of 2 times 4.059 times 10 to the power minus 20 divided by 9.11 times 10 to the power minus 31 is equal to 3.0 times 10 to the power 5 meters per second. And we do that to two significant figures because if you look at our question D as well, the frequency there is two significant figures as well. Okay, so that's our answer there for 2 marks. Quite a bit of work for 2 marks, but again, once you get the hang of it, you can probably skip a few steps and increase your speed and wrap it up quicker. Okay. E. Predict how figure 1 would be affected if the intensity of light incident on the surface were increased. So we've come across this quite a few times, that the light intensity certainly hasn't got any effect on the energy of the photoelectrons that will be released. So increasing the light intensity incident on the surface would have no effect on the graph, as increasing intensity of the radiation doesn't increase the maximum kinetic energy of the photoelectrons. Okay, so remember, instead, more photoelectrons are actually emitted, as the greater intensity doesn't mean more energetic photons. So electrons cannot have more energy. All right, and that concludes this particular lesson on practice questions on the photoelectric effect. I hope it's been useful for you. Okay, there'll be some more opportunities to practice some more questions, and see you next time.